of the people may aware of only first law and second law, right? So apart from this, there are third law of thermodynamics, which is proposed, and maximum M power principle, that is fourth law of thermodynamics, and hierarchically organized systems. Thus, that comes under the fifth law of thermodynamics. So from the first law, we know what is the difficulty with the first law. So it is not talking about the direction of law. So stage by stage, the various advancement in the laws are come into effect. Actually, the scientist Joule defined the term, coined the word energy, right? So we are using this term in our day-to-day life. What is this energy stands for actually? So energy is actually the 1 joule is stands for energy required to lift a small apple 1 meter straight up. So you can understand a small apple, if you want to move upwards 1 meter, how much energy you are spending, that is equal to 1 joule. We can also term it is the energy released when that same apple falls 1 meter towards the ground. So it is the energy released. Again, it comes under joule, or the amount of energy as heat that a quiet person generates every 100th of a second. If anybody is sleeping, that time also he is generating the energy, right? The energy required to heat 1 gram of dry cool air by 1 degree Celsius, that is also equal to 1 joule. So these are all the various means I am defining the joule. 1/100th of the energy a person can get by drinking a single drop of beer, or the kinetic energy of an adult human moving 17 centimeter every second. So these are all the various terminologies for defining the joule. Next, what is this energy? I am starting my lecture with the energy, then I will move to the advanced topic exergy. So energy is the ability to cause work, and work is defined as any useful energy transformation, right? So the most kind of work, one type of energy is transformed into another, with some going into used form and someone may be unused form. You can see some examples how here the chemical energy is converted into light, chemical energy is converted into mechanical energy. So we know that the first law says we can only convert the energy from one form to another form, right? So the first law deals with the amount of energy of various forms transferred between system and its surroundings, and with the changes in energy stored in the system. Suppose I have taken some calories of food inside, I am doing some work. So remaining will be stored as a internal energy. Look at these pictures, there is a potato, right? So the increase in energy of a potato in an oven is equal to amount of heat transferred to it. Suppose if you are giving 5 kilojoule of heat to boil the potato, that will, the potato's internal energy will be increased to 5 kilojoule. And another example, we are not giving any work in the second diagram, so only energy interactions are there. Suppose if you are giving 15 kilojoule heat, only 12 kilojoule is stored as internal energy, remaining 3 kilojoule will be released to the surroundings, right? So the thermodynamics, it treats work and heat interactions as equivalent forms of energy in transit and offers no indication about the possibility of a spontaneous process proceeding in a certain direction. The problem with the first law, as I already mentioned, it is not talking about the direction, right? It is not talking about the direction, whether the high grade energy to low grade energy or low grade energy to high grade, the reverse is possible or not, it is not describing. So the first law does not ensure the process can actually occur or not. So we have to recall this scientist called Carnot and Clausius, right? So the first law main drawback is no restriction on the direction of a process. So the Exergy was first laid down by Carnot in 1824, followed by Clausius in 1865. The energy-related engineering systems are designed and their performance is evaluated primarily by using the energy balance deduced from the first law. However, the first law is the base for writing the energy balance equations. Right, as I already told here, that Clausius only first introduced the term Exergy, but in 1873, Gibbs, everybody knows the Gibbs phase rule, Gibbs defined some parameter called available energy of your body. So what is this available energy of your body stands for? It is the greatest amount of mechanical work which can be obtained from a given quantity of certain substance in a given initial state without increasing its total volume or allowing heat to pass to or from external bodies, except such as at the close of the processes are left in their initial condition. So there will be always some energy will be within the body that he coined as available energy. So from the energy, what are the maximum useful energy that we can generate? That is called available energy, maximum available energy, maximum useful energy. All the are the different terminologies for exergy. Exergy is the available energy when the surroundings are the reservoirs. Exergy is the potential of a system to cause a change as it achieves equilibrium with its environment. So then exergy is then energy that is available to be used. After the system and surroundings reach equilibrium, the exergy is zero. So exergy can be zero. The term, though it was terminologies were used by Gibbs, the term was coined first by Joran Rand in 1956 only, the exergy community effect. But the concept was developed by Gibbs in 1873 itself. Right. So coming to this energy scenario, right? One American consumes 13,246 units, that is kilowatt hour per capita of energy. That energy is equivalent to the energy consumption of 2 Japanese or 6 Mexicans, 13 Chinese, 31 Indians, or it is equivalent to 128 Bangladesh, 307 Tanzanians, 370 Ethiopians. So this is the energy conversion scenario of an American. So Americans eat 200 billion more calories per day than necessary enough to feed 80 million people. So the first law says only energy. So it is talking about the quantity. It is not at all talking about the quality. So all the thermodynamists are interested only in the quality analysis and not on the quantity analysis. Without whatever the thermodynamic analysis, whatever with the efficiency derivation, whatever with the cycle parameters, whatever you are studying, without doing proper assumptions, it will be wrong. It will give only wrong results. So for all the aspects, suppose if you are doing project with the IC engines or any thermal energy storage or any other devices, you have to do only the exergy analysis and not the energy analysis. Energy analysis is not the correct procedure. So because if you are doing wrong calculations and you are making some results, so it can kill the entire generation, right? Thermodynamics, if you give the wrong results, can kill the entire generation, right? In thermodynamics, everybody knows that there is a 6-step approach. Property. So we know what is the property. It's the physical condition of a system. Next, state, process, cycle, energy balance, and performance assessment. These 6 are called 6-step approach in thermodynamics. And the first law of thermodynamics is called as law of energy conservation, and second law is called as law of non-conservation of energy. Okay, so what is this second law says? You cannot even get for all you pay. The first law says whatever you pay, you can get everything, but it is not true. The second law says it is not so. And in thermodynamics, there is called 3S: source, system, and service. And 2S means now people are moving towards sustainable development. So how to store the energy? What are the best methods available? Phase change materials, what are the research we can go for? All those things now people started discussing because everybody interested in the clean environment. So now it moves to 2S: storage and sustainability. So I already told the various terminologies associated with the exergy. So it can be defined in the following means: maybe maximum available work, availability, useful energy, quality of energy, maximum obtainable work, right? True measure of energy quality. So you look at these two simple mathematical equations by which anyone who is new to this exergy concept can understand easily. So everybody knows 2 plus 2 equal to 4. So that is only the energy analysis. But the exergy says the 2 plus 2 will be less than 4 because we are not concentrating on the Exergy destruction part. With some thermal energy is lost to the surroundings, which we are not bothering while doing the analysis, which is not a correct procedure. That is what the second equation says. Right. So in thermodynamics, people know there's only two systems, closed system and open systems. We have some examples for this. We studied this. Closed system, we can tell some rigid tanks, which is completely closed. So only energy transfer will be there. Or we can say the piston cylinder arrangements, another example for closed systems. So everything happens within that piston cylinder arrangements. And open system, of course, we know that the difference is both mass and energy can transfer the boundary. So the best examples are any thermodynamic components, individual components. We can consider nozzles, diffusers, compressors, turbines, and pumps. And what is this USUF? Anybody come across this system? What is this USUF? It is called uniform state, uniform flow process. So I'll discuss in my energy equations. Right. So look at this table. It is for some cold thermal energy storage. Some products I listed here, and carbon to hydrogen ratio also given. So dry wood, if you see this, the carbon to hydrogen ratio is 9, and coal it is 1.63, oil 0.56, methane 0.25, and the hydrogen now it is 0. People now moving towards clean environment because we know the problems with the global warming and ozone depletion problems. So completely we want to remove the carbon in all the thermodynamic systems, irrespective of whether it is household or industrial purpose, refrigerator, air conditioner, or any other power plant cycles, everywhere, any even automobiles, they are completely removing the fossil fuels. Now the research is towards only hydrogen, right? So even you can think of projects in ammonia. If you cool ammonia, we can get nitrogen and hydrogen. The nitrogen can be used for cooling liquid nitrogen, and hydrogen we can use for IC engine fuel cell. Following two equations, we can understand simply what is this low Exergy system for the ORC, organic Rankine cycle. So we know that what is the efficiency, energy efficiency? It is net work output by heat input. So that is expansion work minus pump work by heat input. This is the energy efficiency. Normally in any system, if you calculate the energy efficiency, it will be high. But in case of Exergy efficiency, we have to take the Q input in a proper manner, because whatever the heat you are giving, the high grade energy, something which is lost to the ambient environment, something which will cross the system boundary. So we have to multiply the factor 1 minus TL by TH, which is the correct procedure of calculating the efficiency of any system, which is called exergetic efficiency, not the energetic efficiency. Right. So I request participants, if you have some paper and pen, you just take it. So you listen it very carefully, because this lecture meant for those who are very much interested in thermal engineering. As I already mentioned, if you want to solve any thermodynamics problem, don't simply read and write the given data. You are struggling with getting the solutions. First of all, you should identify what type of system it is, whether it is a closed system or it is a open system or USUF systems, according to which you have to write 4 different equations. First one, mass balance equations; second, energy balance equations; third, entropy balance equations; and fourth, Exergy balance equations. If you are able to write these 4 equations correctly for any system, that means you understand the thermodynamics in a proper manner. Look at this picture carefully. I'm going to explain how I am writing these balance equations. So it is a closed system with a rigid tank. So rigid tank means the mass is not crossing the boundary. So initial mass and final mass are same. So the surrounding is at a temperature, say T naught, ambient. We are giving some heat input, Qi. So, and at the same time, we are doing some stirring action. Within that fluid, we are doing some stirring action using some small pump. So both energies will do some displacement in this rigid tank and some heat will be lost to the surroundings. So this concept we have to understand perfectly, then only we have to go for the balance equations. Looking at this picture, coming to the mass balance, since the system is completely closed, the initial mass will be equal to the final mass. So that is mi equal to mf equal to m. Look at this very carefully. I am using, this is only mass, the unit is kilogram, it is not kilogram per second. If it is kilogram per second, I will put m dot. I am not putting m dot, I am putting only m. So why? Because it is a closed system, mass is not moving, mass is stationary, so its unit is kilogram. Initial mass equal to final mass, mi equal to mf. This is the mass balance. Next I am coming to the energy balance equations. Look at this. So the initial mass mi, the initial mass will have some internal energy. So mi ui, this product is what? One energy. Next, plus we are giving the heat input qi, so plus qi. Again we are doing the stirring action wp. So these are all the inputs to the system, so that comes under the left hand side, miui plus qi plus wp. This is equal to, what is the final change because of this system? There will be a internal energy change of the fluid. So what is that value? Heat value mf into uf, right? Plus I told that heat will leak to the surroundings. Heat will leak to the surroundings, that is QE, right? And coming to the entropy balance equations, if you write the energy balance equations correctly, you can write the entropy balance equations correctly. So miui, now it is replaced by misi, that is mass of the fluid, initial mass of the fluid with the initial entropy. And because of this heat input, we know that the entropy will be generated, class A statement, correct? So heat transfer will cause the entropy to change, so the entropy will be generated. So misi plus entropy generation plus, because of this qi by ts, so it is once again the class is inequality, qi by ts. This is because of the heat transfer qi. This is equal to the final m of sf plus, already qe is rejecting, right? So qe by tb. Look at this. I have written some temperatures here one by one, TB, TSU, TAV, T0. While doing the problems, first you have to see that the correct procedure is whether the boundary temperature is given or not. First you have to see that. If the boundary temperature is not given, because we are not concentrating only on the boundary inside that blue line. So if boundary temperature is not given, okay, at the next, then only you have to take the surroundings, TSU. If surrounding temperature is also not given, then you have to find the average. What is average? Initial temperature minus final temperature. Initial temperature minus final temperature you have to take. Okay, sir, final temperature also I don't know. Then you can take the outside atmosphere. But most of the thermodynamics problems, what we are doing, simply we are taking the ambient, which is not the correct procedure. First, we have to look into whether the boundary temperature is given or not, followed by the surroundings, followed by the average, then only the T naught, right? So next, come to the Exergy balance equations. How I am writing the Exergy balance equations? You look at the energy balance equation, second equation, and this Exergy balance, both are looking symmetrical. So simply we are replacing the U by E, Exergy. So MIEXI, because of this initial mass of the fluid, plus because of this heat transfer QI, there will be a thermal exergy. E suffix X, QI is called thermal exergy. Next, because of this stirring action, we have another exergy due to the work, WP. This is equal to, it will cause some change in the system, right? So that is called MFEXF, right? Plus, look at this diagram, some heat is leaving to the surrounding, plus EXQL, that is thermal exergy lost to the surroundings because of the heat transfer, that is called EXQL, plus exergy destruction. In any system there will be exergy destruction like the entropy change. Okay, so that we have to take into account. So where EXQ is the thermal exergy, small, if I use the small letters, that is called the specific exergy. So you know the units. Specific means kilojoule per kilogram and exergy means kilojoule. And if you put exergy, ex dot means that will be the exergy rate, that will be kilowatt. Okay, so how to calculate this thermal exergy? Exq is nothing but 1 minus T naught by Ts into Qi. In energy efficiency equations, we are using only Qi, correct? We are not bothering about this term 1 minus T naught by Ts, but exergy we have to take into account. That is the correct procedure. And similarly, in the final, 1 minus T naught by T boundary. In the first equation, it is Ts means system because it is inlet, and Qf is the final. So we am taking the boundary. Okay, what is this exergy destruction? This is nothing but T naught into entropy generation. T naught into entropy generation. How we are writing delta S equal to dq by T? Second law, class is inequality. Same way we are writing exergy also energy, that is heat unit only. So exergy destruction is T naught into S gen. Since it is a closed system, we are not using the enthalpy terms. Listen very carefully. So enthalpy is the term associated with only the flow, that is open systems. We are solving the equation with only the internal energy because it is a closed system. So what is this specific exergy at inlet? EXI is nothing but UI minus U naught minus T naught into SI minus S naught. Similarly, for final, you just replace I with F. I means initial, F means final. Okay, so now you can understand how to write the balance equations for a rigid tank. Next, this is another example called piston cylinder arrangement. We are using in the many applications, even IC engines. Here they are giving some heat, so that definitely the internal energy of the system changes. So there will be because of this heat input, there will be a boundary work WP. And whenever heat is a high grade energy and work is a low grade energy, there will be always a loss, correct? So QE is the heat rejection. If you have to draw the diagram perfectly, then only you have to write the balance equations, then you have to solve the problems. So what is this mass balance equations for this? Right, since the system is completely closed, piston cylinder arrangement is completely closed, so Mi equal to Mf. Next, energy balance equations. Because of this fluid inside with the internal energy, so Mi Ui plus I'm giving the heat input, so Qi. These are all the input which is on the left side. This is equal to what is, because of this, what are the changes we are observing? There will be the internal energy change within the system, that is called Mf Uf plus boundary work. Wb is the boundary work, and since heat is the high grade energy, there will be some rejection, that is called plus Qe. Right, this is called the energy balance equations. Right, and this boundary work, it is nothing but a displacement work. So since it is a constant pressure, because it is completely closed, so instead of Wp, you can write P into V2 minus V1, displacement work. So that is the second equation in another form. Next comes the entropy balance equations. As I already told, I'm writing the entropy balance equation from the energy balance equation. I'm just replacing U by S, Mi Si, that is initial entropy, plus because of this change, there will be entropy generated, S gen, plus Q is entering inside to the system at a temperature Ts. So because of this heat transfer, entropy, because we know that for irreversibility, one of the reason is heat transfer. So Qi by Ts, these are all the inputs of entropy. This is equal to, because of this, what will be the changes in the entropy? M of Sf within the system, plus crossing the boundary is Qe into Tb, Qe by Tb. This is the entropy balance equations. Right, next, exergy balance equations. Right, so instead of U, we are replacing by E. Okay, so Mi-EXi, that is initial exergy, plus what is this term? Capital E suffix XQi, thermal exergy due to the heat transfer Qi. This is equal to M of EXF, though this Mi-EXi will become M of EXF final, plus you can see the boundary work. So plus boundary work, plus there is a heat loss to the surroundings, that is called thermal exergy. In superscript, we are seeing the QL or QE, right? Plus always exergy destruction will be there, right? And previously I told the closed system for rigid tank, there we had that specific exergy as U terms minus T into S terms. But here we have to add the plus P naught into V1 minus. Now why? Because we have the boundary work here. So plus when we are solving the piston cylinder arrangements, we have to include the boundary work. So plus P naught. P naught is the pressure, stagnation state pressure into V1 minus V naught, right? Dead state. And similarly at the final, right? Next, this is the another closed system. What we are seeing here is there is a water bath which is at a low temperature, in which we are suddenly putting some steel bath and iron bar which are at a very high temperature. So what happens? Quenching will take place. So over a period of time, this solid steel bar or iron bar will reach to the temperature of the water, thermal equilibrium, right? So how to write these equations? So because of this system, because the system is completely closed in its boundary, the mass of the water is not escaping, right? So mw1 equal to mw2. Similarly, the iron piece, it is not going to leave that system boundary. So sb1 equal to sb2. Similarly for the iron, right? So that means mt1 equal to mt2. That is the total system mass remains constant. Next, the energy balance equation. Since it is a closed system, we are taking only the internal energy. So for water m1 u1 and iron m1 uib1 and steel bar msb1 ub1, this is equal to the outlet plus the earlier loss ql. Okay, and entropy balance equations, we are just replacing the u by s. For water mw1 sw1 plus for steel bar msb1 sb1 and for iron bar mib1 sib1. And because of this temperature changes, there will be entropy generation. This is equal to the final state properties, that is water, steel bar and iron bar, plus there is a heat leakage, correct? Because the system, we are undergoing the thermodynamic cycles, right? So there will be a heat loss to the surroundings. So that is QL by TB. That is another entropy term. And next comes the Exergy balance equations. Once again, we can derive from the energy balance equations, replacing the U by E. So MW1 EX1 is the total exergy of water. So mass of water multiplied by specific exergy of the water. Total exergy of the water at inlet. The second term, total exergy of the steel bar at inlet. The third term, total exergy of the iron bar at inlet. This is equal to total exergy of water at outlet, total exergy of steel bar at outlet, total exergy of iron bar at outlet, plus there is a heat loss. Look at the diagram. So thermal exergy loss plus exergy destruction. If you look at all the equations, nowhere I am using the dot symbol. Normally in thermal engineering, when you put a dot in terms of kilogram per second, so flow will be there. That is only in the open systems that we are going to discuss next. Right. So open systems. So open system, what is the meaning of open system? There will be a mass flow rate will be there and energy will be there. So mass flow rate means we are not going to use m. We will be using m dot, right? So mass also we are crossing the boundary. So this is a simple nozzle, for example, that any gas or steam enters at 0.1 and leaves at 0.2. Okay. So what is the mass balance? Steam nozzle or any device. So total mass at inlet equal to total mass flow rate at the outlet. Continuity equation m dot 1 equal to m dot 2. And what is the energy balance equation for a nozzle from steady flow energy equation? So m dot 1 h1 plus v1 square by 2. This is equal to m dot at 2 h2 plus v2 square by 2. This is the well-known steady flow energy equation for a nozzle. So we are eliminating all the heat transfer and work transfer terms because nozzle is only a energy transformation device, not energy transfer device. We are not getting any shaft work. Okay. And the entropy balance. So nozzle, definitely the entropy will be there because H is there, enthalpy is there, flow energy is there. So because of that, entropy will be there. So m dot S1, that is the total entropy at inlet, plus because of this flow, entropy will be generated. Nozzle always friction will be there. So entropy will be generated. This is another reason for irreversibility in the process. So entropy will be generated. This is equal to m dot into S2 final. And similarly, I told Exergy balance equations. We are just closed systems. We replaced the U with the EX. Here we are replacing the H with the EX. Okay. So m dot EX1 at inlet equal to m dot EX2. That is the Exergy balance. Plus we have to take into account the Exergy destruction. Exergy destruction, how to calculate? It is nothing but T naught into S gen. Okay, so we know the outside temperature multiplied by the entropy generation will give the Exergy destruction. This is the balance, mass balance, energy balance, entropy balance, and exergy balance equations of a simple nozzles or diffusers. Okay, nozzle and diffusers are reverse. Next, we will see one by one the energy transfer devices. So nozzles and diffusers are the energy transformation devices. There is no shaft work in or out, whereas the compressors and turbines are the energy transfer devices. Okay. So let us start with the compressor. Any air or any fluid is flowing. So at the initial state and final state, the mass flow rate is same. So m dot, I am using the symbol m dot, not m. So while writing the equations in thermodynamics, even if you make a small mistake, it will lead to a wrong results, right? So it is a open system. Flow rate will be open system. Another name is flow process, right? So flow means kilogram per second mass. So that is why we are using m dot. Okay. So m dot 1 equal to m dot 2, compressor inlet and outlet. Next, if any fluid is moving through the compressor, you imagine the refrigerator or any other device, it will move with the some initial energy, that is m1h1, m1 dot h1, that is the initial energy. Plus, to run the compressor, we have to give the power. So plus wc dot, work input power. This is equal to what? M dot 2 H2 plus heat transfer loss, because W is a low grade energy and heat is a high grade energy. As per thermodynamics, low grade energy to high grade energy is not possible. So there will always be a loss. That is why Q dot E. Okay. Next, the entropy balance equations, very simple. M1 dot S1 instead of H1, S1 plus entropy generation. Okay, this is equal to at outlet M2 dot S2. That M1 dot S1 is converted into M2 dot S2 plus there is a compressor heat leakage outside. So that will be that entropy we have to take into account. QE dot slash TB. Look at this. I'm using TB. Why? I told that we have to take first the boundary temperature. It is not given, then only we have to go for the surroundings or average or TS. Okay. Next, Exergy balance equations. We are just replacing the H with the EX. So M1 EX1, M1 dot EX1 plus W dot C equal to M2 dot EX2 plus thermal exergy, because heat is released to the surroundings. Thermal energy loss, that is capital E dot X QE, nothing but thermal exergy loss due to heat transfer, plus exergy destruction E suffix D, EX suffix D, that is equal to once again T naught into entropy generation. This is for the compressor. What about the turbine? If you are able to write the equation for compressor, you can write it for the turbine, because compressor and turbine are, one is power absorbing and another one is power producing, right? So for turbine, M1 dot equal to M2 dot, same like compressor, but energy balance equations here, there is a mistake actually. That WC dot won't come actually, right? So M1 H1, M1 dot H1, this is equal to M2 dot H2 plus turbine work, W dot T, turbine work. Okay. Then what is this Q dot E?
Senthil sir.
Hello.
Sir, are you there?
Yeah.
Okay. Carry on. Hello.
Sir, shall I proceed?
Yes, sir.
Okay. Turbines, that entropy balance equations will be M1 dot S1 plus S generation. This is equal to M2 dot S2 plus QE by TB, boundary temperature. Similarly, the exergy, we have at inlet only the inlet exergy, M1 dot EX1, right? This is equal to M2 dot EX2 plus turbine work, exergy due to the work transfer. Next, exergy due to the heat to the condenser. Next, exergy destruction rate. Now look at the last two equations. Specific exergy at inlet, small letter, I am using specific exergy. Specific exergy at inlet and specific exergy at outlet, I am using H1 minus H0. If you remember that closed systems, I just used U1 minus U0. because closed system there is no enthalpy. We know that enthalpy is what? U plus PV. That is, enthalpy is internal energy plus flow.
Sir. Hello. Sir.
Using in the thermodynamic systems, for which the mass balance equations will be m1 dot pump, you know, whatever the water you are extracting, same water is coming out. So m1 dot equal to m2 dot. And what is the inlet? From low grade, we are lifting to the high grade. So m1 dot h1 pump, which needs the energy input, so which will be on the left side. Wp dot. This is equal to this combinedly used to lift the water. So m2 dot h2. What is the pump work formula? We know that m dot v into delta p. Okay, so that is m dot v into delta p is p2 minus p1. Next, the entropy balance equations. Pump, it is very simple. That is inlet entropy plus entropy generation. This is equal to the outlet entropy, total entropy at outlet. Similarly, Exergy balance equations, I am just replacing H with Ex. How closed system I am replacing U with Ex. Here in open system, we are replacing H with Ex. So that is M1 dot Ex1 plus pump work dot. This is equal to at outlet M2 dot Ex2 plus Exergy destruction rate. Next, if you look at this, there is a heat exchanger with the two fluids. Okay. So for cold fluid or hot fluid, if you see the mass balance equations, for any fluid, the mass flow rate remains constant. So M1 dot equal to M2 dot. For hot fluid, inlet and outlet, mass flow rate is same. And for cold fluid, M3 equal to M4, mass flow rate remains same. So coming to the energy balance equations, we can tell easily. For example, M1, let us assume it is a counterflow heat exchanger. M1 dot H1 is the, let us say, hot fluid inlet. M3 dot H3 is the cold fluid inlet. This is equal to hot fluid outlet plus cold fluid outlet. So these are all the total energy terms. So M1 is M1 dot multiplied by the specific enthalpy will give the total energy. Next, entropy equations, M1 dot S1 specific entropy into M1 dot plus similarly for the another fluid M3 dot S3 plus we have to take the entropy generation. Okay, so even a small temperature difference will cause entropy to generate. We know that. That is why we are not able to operate Carnot cycle still. Right? This is equal to M2 dot S2 plus M4 dot S4. That is the hot fluid and cold fluid at the outlet. And the last one is the Exergy balance equations. Similarly, for hot fluid and cold fluid, I am just replacing the H with the Ex. This is equal to again hot fluid and cold fluid at the outlet M2 dot Ex2 plus M4 dot Ex4 plus the Exergy destruction rate. That is a T naught into S gen. That is EXD. And in thermodynamics, we are seeing that adiabatic mixing or mixing chamber, some two fluids are coming in different streams and they are joining together. So in this case, all are the moving. So it is a open system. So M1 dot plus M2 dot equal to M3 dot, which is the mass balance equation. Next, the energy balance equation will be M1 dot H1 plus M2 dot H2. This is equal to M3 dot plus into H3. Okay. Next, entropy balance equations, M1 dot S1 plus M2 dot S2 plus entropy generation. This is equal to M3 dot S3. Exergy balance, simply you change H with S and finally you have to put the destruction. So M1 dot EX1 plus M2 dot EX2, this is equal to M3 dot EX3. After mixing M3 dot EX3, final Exergy rate plus Exergy destruction. And in refrigerator and in applications, we can see expansion valve and small cylinder. So expansion valve, it is almost equal to a throttling process. So mass balance equation will be M1 dot equal to M2 dot. That's all. And for expansion valve, what is happening? As already told, it is a throttling process. So H1 equal to H2, right? So when it comes to total energy, it will become multiplied by M dot. So M1 dot H1 equal to M2 dot H2, that is for expansion valve. And the entropy balance equation, similarly replace H by S, M1 dot S1 plus entropy will be generated whenever fluid passes through a small restrictions. This is equal to M2 dot. So all the open system, if you look at very carefully, I'm using M1 dot, M dot 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 because it is a flow system, not a closed system. Closed system, it will be m kilogram, but in open system it is m dot kilogram per second. And in closed system we are using only the internal energy U, and in open system we are using enthalpy H. Okay, and this most of the people may not be come across this process USEF. This is called unsteady uniform state uniform flow process. Uniform state uniform flow process. Okay, we studied about what is the closed system. We studied about what is open system. So either the system may be, it may admit mass or it won't. Accordingly, we are naming it is open system or closed system. But in some systems, what we are doing, I am just filling and I am discharging. For example, two-wheeler tire, we are filling, we are inflating air, we are removing the air. So initially the air is inside, now it is closed system, correct? But while you are filling, according to the time, it will vary. So it is open system, correct? So uniform state, uniform flow process, it is nothing but a combination of closed system and open system. If you look at these equations, you can understand very clearly. So there is a tank, okay, with the initial mass mi, that is unit is kilogram, plus let us assume the tank is filled with some gas. So I am filling for 5 minutes or 10 minutes. So that is called what? Mass flow rate, m1 dot. Now you see this, the mi is what? Kilogram, but m1 dot is what unit? Kilogram per second. So equation is not balancing. So we have to multiply by the time scale. So m1 dot into delta t. How much time I am filling the tire? Okay, now the units are, all units are what? Kilogram. This is equal to final mass, correct? Similarly, the energy balance equations, first the tire is with less air. So it is internal energy only, closed system. So MIUI. Next, I am filling the tire with air. So it is open. So it is not U, it is H. So M1 dot H1, how much time I am filling? Delta T. So this M1 dot H1 delta T unit also equal to MIUI. You can write and you can try. Okay. So both are kilojoules only. This is equal to final mf uf plus energy lost to the surroundings. Okay, due to temperature variations, you can see this temperature, there will be a drop in the air pressure, right? So that is thermal energy lost to the surroundings over a period of time. Next, entropy balance equations. Initially it is a closed system, so MISI plus M1 dot. Now it is open system. I am filling M1 entropy generated because of this pressure, M1 dot S1 into delta T, plus in any system because of this irreversibility, entropy will be generated. So S dot generation, entropy generation. This is equal to final entropy plus that entropy transferred to the surroundings because of the boundary temperature over a period of time. Next, Exergy. If you're writing the energy balance, you can write the Exergy balance well. As I already told, you just replace U by EXI and H1 by EX1, and but don't forget to include the Exergy destruction rate. Okay, now actually this is not Exergy destruction rate, it is Exergy destruction only because we are just multiplying by delta T. Okay, and we know that the thermal power plants operating on the simple Rankine cycles. So far we have used the term efficiency is nothing but the useful output by total input, turbine work minus pump work by heat input. And the second equation Exergy, okay, W net by Exergy input we have to consider. So if you use QC as useful output, okay, what I'm trying to say here is from the power plant's turbine, the heat is rejected to the condenser. That heat also I am taking as useful work, for example, because I am talking about Exergy, not energy. So in that case, that QC will come under the numerator, W net plus QC divided by total heat input. So like this, we can write the energy efficiency and Exergy efficiency. And combined cycle also, like this condenser, again we are using the waste heat, once again organic Rankine cycle. Like this, if you add all the outputs from the power plants, all will come as a output in the numerator divided by the given heat input. Okay. And this is another thermodynamic systems called refrigeration, and Kelvin contributed for the heat engines, and Clausius contributed for the refrigerators and heat pumps. All right, Clausius statement and Kelvin statement, we know that. So for performance, we are using this term coefficient of performance, COP or suffix en ex, that is energy based and exergy based. For COP of refrigerator energy based, it is Q by how much heat it is removing with the given input, work input. And exergetic means we have to talk about the thermal exergy, how much is removed with the given input. And similarly for the heat pump, it is reversed. Instead of evaporator, you are using the condenser. Okay, because system and surrounding are reversed here. Okay. So what is this thermal exergy formula? It is, as I already told in many equations, it is 1 minus T naught by Ts times the heat input. This is how we are joining the first law efficiency and second law efficiency. Okay, for heat engines, and for refrigerator it will be reversed, T naught minus Ts, because in refrigerators it is not the efficiency, it is the coefficient of performance. We are using the power input to achieve, whereas in engines we are getting the power inputs. So far I have taken some closed systems, rigid tank, piston cylinder arrangement, quenching of some hot elements on the water bath, and in open systems, nozzles, diffusers, turbines, compressors, heat exchangers, mixing chambers, pumps, expansion devices, and uniform state, uniform flow devices, how to write the balance equations. So hereafter, whenever any thermodynamic problem, suppose you want to solve, first you write all the 4 equations, try to write 2 times, 3 times, you try to write the equations, then substitute the given data, you will get the correct answer. This is the best procedure of solving thermodynamic problems. Okay, so these are all the thrust areas associated with the thermal energy storage systems. So a lot of projects, government funded projects are going on in this field. Those who are interested in thermal engineering, they can think of these areas: thermal energy storage systems, thrust areas, pumped storage, electrochemical batteries, flywheels we are using for storage, compressed air, biological storage, magnetic storage, even some light can move the particles, right? So magnetic storage, chemical storage, thermal energy storage, nano level storage, phase change materials with carbon nanotubes, CNT, sensible heat storage, example earth beds, water tank, solar ponds. These are all the some thrust areas where lot of projects are now available. Next, latent heat storage. Latent heat storage, now we are using salt hydrates as PCM. We can also use organic materials. Okay, heat transfer fluid with 15% glycol water mix in polypropylene piping with the pressure 350 psi, and battery thermal management system applications by PCM. PCM with 3% carbon nanotubes, PCM with 6% carbon nanotubes. These are the some latest research associated with the thermal energy storage system. Why I have taken this slide here? Because everyone is moving towards green environment. We have to store the energy. Now hydrogen is going to rule the world. So the future is going to be with hydrogen only. So we want to eliminate completely carbon, right? So better devices, fuel cells, we have to think of, okay, we can search some materials related to all these hot topics so that we can think of some projects. And based on my presentations, what are the concluding remarks I want to tell? Energy is only a quantity. No thermodynamic analysis is interested on quantity. It is interested on quality. All are doing some biodiesel work or any other work, simply writing some efficiency equations, and they are writing some proposals or writing some papers, right? So that people has to think that is not the correct procedure of getting the efficiency and all those things, because we are completely forgetting the environmental effects. We are completely forgetting the exergy distractions. We are completely forgetting the exergy terms, useful exergy. So hereafter you have to take into account the second law efficiency based analysis. Okay, so you can search this some papers on available in International Journal of Energy and Research, a review on clean energy solutions for better sustainability. Now the entire world is moving towards sustainability, right? So we want the clean environment. So next, thermodynamics, a smart approach by Wiley Publications. Thermal energy storage and its applications by Professor Ibrahim Dinser from Wiley Publications. Low energy systems for high performance buildings. Okay, and now you know how to write little bit the balance equations. And one more thing I want to stress here: exergy can be negative, but exergy destruction cannot be negative. Okay, because exergy destruction is T naught into entropy generation. And now you know how to write if a system is continuously changing with respect to time, the mass flow rate or energy flow rate is changing, that is filling and discharging of tanks, uniform state, uniform flow process, how to write the balance equations, for which the literatures available are very less. If you are able to write this type of equations, it will be good. And enthalpy of formation and enthalpy of combustion, you can think of how to write the exergy balance equation. Second law analysis of reacting systems, and exergy analysis of heating, refrigeration, and air conditioning systems. Exergization. What is exergization? Use of exergy as a tool for energy research. That is called exergization. Hydrogenation, and use of solar energy for hydrogen reduction. Solar methane cracking. Okay, so from methane we can extract hydrogen using solar energy. That is called solar methane cracking, because the atmosphere contains huge amount of methane, by which if you use the solar energy effectively, we can produce hydrogen. Solar concentrated coal fired supercritical thermal power plants. Gone are the days we are using still steam for producing the power. So people are moving 100% solar concentrated coal fired supercritical. So about 200 bar, you can operate the thermal power plants with the help of simply solar power. And the government approved these refrigerants now, R134A and 143A. These are the latest refrigerants being used. And we can use photovoltaic semiconductors exposed to sun visible solar radiation 40%. And we can think of projects on energy audit, identification of waste in industry. In some countries like Sweden, for example, there is no waste at all, because whatever the waste they are from the household, they are collecting the waste. All the waste are used for producing the power 100%. So there is no landfills, there is no waste you can see outside in these countries. So our countries, we are seeing lot of landfills in many places. Waste management system is very, very essential for a country like India. So complete energy audit is necessary for sustainable development. So I thank the Chalapathi Institute of Technology for giving me an opportunity to share the Exergy related aspects to the mechanical engineers. So once again, thank the management. If any queries, I given my email ID. You can write your questions to this email ID. Definitely, I will answer to the maximum possible extent. Thank you.
Thank you, sir. If you have any questions, you please raise your hand. Otherwise, chat box is open. You are able to chat in the box also. You post the questions in chat box also. Anybody is there? Please raise your hand. Durga Prasad garu.
Sir, good evening, sir. Sir, I want to
Good evening.
know. Sir, I want to know fourth and fifth law of thermodynamics, sir.
Yes. Fourth law of fifth law of thermodynamics, right?
Yes,
So
sir.
now the what is this first law says? It is only conversion from one form to another form. It is not talking about the direction, right? The
Yes, sir.
second law says it is not possible. The first law is wrong. The third law talks about the exergy. So what is this maximum empower principle is with the available energy resources, you have to produce maximum output. Okay.
Yes, sir.
Suppose if any organization is running, okay, any dairy industry or any power plant industry, okay, for optimum efficiency, whatever the results, whatever the resources available within this firm or industry, with that they have to think for the better exergy output, better efficiency output. That is called maximum empower principle. Okay, some industries started working on, if you work on an organized manner, that is the fifth law. If any system, if you work on, as I already told you, if you are doing any thermodynamic analysis, the assumptions are very important. According to the assumptions, you can get the results, correct? So the assumptions should be reliable. This is what the fifth law says. So we have to consider all the very small facts. Even we know that a small 1 degree temperature will cause entropy change, correct? But theoretically in textbooks, all those things we are not studying. When you come across some practical industries, even a small temperature difference will cause a huge energy transfer. So that is why people nowadays interested only in the exergetic efficiency and not on the energetic efficiency. Most of the ice plant and the dairy industries, they start working on the fifth law. That is, if you have a hierarchically organized systems, they can have the maximum exergy output. Okay, so what are the various possible ways by which the energy is lost that they have to consider and they have to minimize? Suppose if any fluid is there, I want to lift the fluid, I want to change the temperature of the fluid, whether I have to go for the compressor or I have to go for the pump, right? So both may function same, compressor or pump may function same, but which device will consume less power, which device will handle less volume, all those things we have to concentrate. But in thermodynamics, we are not concentrating all those things. Simply we are putting compressor instead of pump. If some process is possible by pump itself, particularly while handling the liquids, why we have to go for the compressors? So this is what this law moves like this, fourth law, fifth law. Hello?
Oh, okay, sir. Thank you, sir.
Thank you, sir. Hello?